Hi guys, welcome to our channel of Sciences and Mathematics. We're going to do a second part of the topic of kinetics that we have done, of course, in the introductory part regarding the definition of specific concepts and the terms that we use. And of course, we looked at the various ways in which we do graphing of kinematics, of course, which entail the velocity time graph, acceleration time graph, and then displacement time graph. In this case, of course, in deriving kinematic equations, we're going to use a particular kind of a graph, maybe which will assist us to find the relationship between different equations which we're going to look at. So without further ado, thank you and welcome. So in that case, we have said that we are going to deal specifically with the deriving of kinematic equations. So, and these equations are going to rely on the concept that all of them will presumed to be derived from the concept of uniform acceleration. And we're going to use the, of course, velocity time graph of a uniformly accelerated object. So we are going to use a velocity time graph of a uniformly accelerated object. So which means we talked about uniform, of course, uniform acceleration for the velocity time graph, and then there was an ununiform one that looked like an exponential curve, which was like this. So this is the time against velocity. So for the acceleration, we said that that one was non-uniform, and in that case, we're going to use the one that we had uniform acceleration. So that is what we mean that the change in acceleration against time is a constant one. So in that case, we shall use these two aspects that considers uniform acceleration and velocity time graph that we have shown, the latter one that we have shown. So in that case, I just draw that graph so that whenever we are going to explain some concepts, we are going to refer to the graph. So that one will be a general one, and we shall be using initials, which we are given when we were defining in our first set of the first discussion. We were defining some terms. So I'll just be using initials, but we shall explain what they stand for. So for that case, we just draw a graph there, and put those dotted lines. We're going to derive some information from there, and then put that dotted line there. So this is a velocity time graph, which is denoted by the initials V for velocity and T for time. So in this case, I'm going to shade this area which is under the curve, and then this I'm going to indicate U, implying that this is initial velocity. Maybe the object started at this point, and this is the final velocity. So this is a velocity scale, and this is a time scale. So at this point, it will be from 0 to time t. So and if I can just put at this side a small, of course, set of what we have discussed. So for S, initial S that we are going to use, that one will denote displacement. And then for U, I've said that one will denote initial velocity. And then for V, this one will denote final velocity. And then for A, we're going to use A to indicate acceleration. This one we have mentioned earlier, the initial A will stand for acceleration, and T for time respectively. T is going to stand for time. So in that case, those are some of the initials that we're going to use to interpret this graph, bearing in mind that at this point O is the origin. So in that case, we're going to look specifically at 4 equations, so 4 kinematic equations, and try to see how maybe displacement, velocity, and then maybe acceleration can be represented. So we said for a velocity time graph, the area under the curve gives what we call displacement. So this area gives what we call displacement. And we're going to look at that. Of course, we have denoted displacement by the initial S. So from normal mathematics, we can just look at this specific area under the curve and say that it's a regular figure, of course, which we can use the common formula that we have. It's a trapezium, so we can use a common formula that we have to find its area, bearing in mind that we can use these letters to indicate the distance. So in that case, we can see that there is a triangle at this particular point. So this one we can find it using the area of a triangle. And this one particularly, if it's a square or maybe a rectangle, then we can find the area, which is length times width. Now for this is a half base times height for the triangle. So the total area for this will be length times width plus a half base times height. So let's try to see using the initials that we have done how we can find this area. So as we have said that displacement is represented by the area under the curve. So S will be area of the triangle plus area, let's say area 1, area 2, area of the rectangle. Area of the triangle plus area of the rectangle. Or maybe we can just commutatively indicate the one against the other. A plus B is the same as B plus A, so we can start with any. So for the sake of just uniformity, we can just start with the area of the rectangle and then the area of the triangle. So as we have said, we are just going to use this initial. So for this case, the area, as we said, is length times width, having identified that this segment below here is what represents the triangle. So in that case, the width for this case is the length. The width is from point O to T, I mean from O to U, and the width is OT, which we can represent as U times T. So the area for the rectangle is UT. And then for this other one, it is a half times base. Base is T times height. So this one times height, which is V minus U. So the distance between this point and this one is V minus U. So we shall have V minus U. So trying to make, of course, a rearrangement for this, so just trying to simplify it. And this equation will be reduced to UT plus T over 2 V minus U. Or just, okay, we can just indicate like that. This is V minus U so that it does not give us a confusion. So in this case, the displacement is given by the expression SU plus T over 2V, which is final velocity minus initial velocity. So that expression, of course, gives us, if we try to do a simplification for that, it will just give us, by expanding that set of information that is inside the brackets, we will get that S is represented as average velocity, which is U plus V over 2, indicating average, times T. So this is the first equation, our first kinematic equation that is representing displacement, and we're going to apply that one in case we come across it. So remember that this will be a first expression, of course, because of the size of our space for evaluating or calculating this. We'll just try to erase this, but remember that is the expression, the first expression, so which indicates the displacement, whereby we have said that the total displacement is equals the area under the curve, which is area of a trapezium that is made up of area of a rectangle plus the area of a triangle, which we have done using the normal mathematical way of operating that. So there's addition of the two areas of a rectangle and a triangle. So that's the first set indicating displacement for S. So I can just write there, so for the sake of uniformity, that we have found that one using the other parameters that we have been given. Now in this case, for velocity time graph, of course the gradient will give us acceleration, and acceleration, as we said, that it is change in velocity, which is final velocity minus initial velocity divided by time. So that one is an equation that is going to be applied. So making a rearrangement for this, we can make v the subject of the formula by multiplying both sides by t and then minus u. So it will be at is equals to v minus u. Making v the subject of the formula, we shall have v is equals u plus at. So this representing final velocity, which is v, is given by the equation of v is equals to u plus at. So this particular equation gives us a second set of another kinematic equation for constant acceleration that we give for this kind of a graph. So in that case, that is the second kinematic equation, apart from the one for displacement. This is the second that we've already derived. So bearing in mind that acceleration, which is the slope of this graph, is given by the change in velocity over time, that is final minus initial divided by time. So that one is the second set of a kinematic equation. So moving to the third one, we said that the area beneath the v, the velocity time graph, is displacement, which we had given, of course, as we were deriving S, we had given S as initial velocity times time plus, this was average velocity times time, which is final minus initial. So in that case, from the second equation that we have derived over velocity using acceleration, we have said that v is equals to u plus at. Now we can find another representation for v minus u from this particular equation by just bringing u to the other side and say that v minus u is equals acceleration times time. So final velocity minus initial velocity is equals acceleration times time. So for this case, we shall substitute this one at this particular point and see which kind of an equation we come up with. So we use that one at at this particular point and say displacement is equals to ut plus t over 2 into at. So we have substituted this one for at from our second equation. So let's see, this one will give us an equation of this kind, which is S is equals ut plus a half at squared. So this is our second way of representing displacement. So this one will give us a third kinematic equation, apart from the first one that we had seen. This equation, of course, will be our third kinematic equation, of course, which we were supposed to derive. And lastly, we shall look at a way of representing v. We are given v as u plus at. So we shall look at another way of representing v, which is final velocity, from this set of information. So we are going to say that our final derivation of the S that we had written for displacement we gave it as initial plus final over 2 times time. So that was the average velocity of displacement or times time. And then we had said that v is equals u plus at. So looking at this as well, we can make t the subject of the formula so that we can make a substitution at that point. So we can say that this is v minus u. We have just changed that one from the other side. It equals at. So making t the subject of the formula, we shall have t is equals v minus u over a. So in that case, we're going to substitute this value for t at this particular point. So it is v minus u over a. So another way in which we are going to represent this one is s is equals u plus v over 2 into v minus u over a. So evaluating for that, we will have s is equals v squared minus u squared all over 2a. So that one making v the subject of the formula, of course, because of space, I just write the answer for that. V squared is equals u squared plus 2as. So that one will be v squared equals u squared plus 2as. So that one will give us the equation number 4, kinetic equation number 4, which leads us to the last bit of the kinematic equations that we were deriving from the velocity time graph, of course, which is indicating constant acceleration. So in that case, these 4 sets of equations, I'm going to write them in summary and do away with this. So that we can be able to see the 4 kinematic equations that we have been able to derive. Just leave those ones there. So the first kinematic equation that we have derived was s is equals u plus v over 2 into t. This was our equation number 1. And then the second kinematic equation we have derived was v is equals u plus at. So this was our equation number 2. And then the third kinematic equation we have derived was s is equals ut plus a half at squared. This was equation number 3. And then the last equation that we have derived was v squared is equals u squared plus 2as. So these 4 sets of equations represent the kinematic equations, of course, which are derived from the velocity time graph. I represent 4 sets of equations which are describing this motion, of course, kinematic motion of a constant acceleration. And of course, as I have said, we have derived them from the velocity time graph. So this equation, we are going to mention them as we go by under the topics which are related to kinematics, or some other topics which might borrow from the concept of kinematics, so that they will assist us in solving some of the problems which are kinematic related. So in that case, for today, thank you guys. So these concepts, try please to remember them so that when we come across them, we shall be quoting and remembering. But in any case there is need, we shall be putting a link to this video to that information, so that we are able to just try and remember that and maybe solve a problem or two. So for that case, that is it for today. Thank you. Bye. God bless you.